For 7 decades, the most powerful computers on Earth have been prisoners, trapped inside steel vaults chilled to temperatures colder than the vacuum of deep space, drinking millions of dollars in electricity just to stay alive for a single calculation. Scientists called this the Great Wall of Quantum Computing, the wall that everyone agreed could not be broken without unimaginable cost, unimaginable infrastructure, and unimaginable patience. Stanford University just walked straight through it, and the world of computing will never look the same again. Every single quantum computer that exists today, whether it sits in an IBM research facility, a Google lab, or a government-funded supercomputer bunker, operates under one brutal non-negotiable condition. It must be frozen, not refrigerator cold, not Arctic cold. We are talking about 15 to 50 millikelvins, a temperature so extreme that it makes the surface of Pluto feel like a summer afternoon by comparison. The universe itself, in the cold emptiness between galaxies, sits at about 2.7 Kelvin. These machines run colder than that. They run near what physicists call absolute zero, the theoretical floor of all temperature, the point at which atomic motion itself nearly stops. And the reason for this is not some engineering quirk that smarter people simply haven't solved yet. It is fundamental to how quantum computers work, or at least it was until now. To understand why Stanford's breakthrough is so staggering, you first have to understand what quantum computers are actually doing that requires such insane conditions. Classical computers, the ones in your laptop, your phone, every server farm powering the internet, store and process information as bits. A bit is either a 0 or a 1, binary, on or off. It is the most basic unit of information, and classical computers chain billions of them together to perform calculations. Quantum computers work on entirely different physics. They use qubits, quantum bits, and qubits can exist as 0, 1, or both simultaneously, a phenomenon called superposition. 2 qubits do not just represent 4 states, they represent all 4 states at once. 10 qubits represent over 1,000 states simultaneously. 300 qubits, in theory, represent more states than there are atoms in the observable universe. This is why quantum computers can solve certain problems millions of times faster than any classical machine. But there is a catch, a devastating civilization-scale catch. Qubits are almost impossibly fragile. The quantum state that makes them so powerful is also what makes them so vulnerable. The instant a qubit interacts with any form of heat, any vibration, any random thermal energy from the environment, it loses its quantum properties in a process called decoherence. The qubit collapses from its powerful superposition state into a simple, ordinary classical bit. And your revolutionary quantum computer is now just an extremely expensive and complicated piece of junk. This is why the cooling is necessary. At temperatures near absolute zero, thermal noise drops to almost nothing. The qubits can maintain their quantum state long enough to actually perform a calculation. But the price of that stability is brutal, and the numbers are almost offensive when you look at them clearly. A single dilution refrigerator, the specialized cooling apparatus that maintains a quantum processor at those near absolute zero temperatures, costs anywhere between $300,000 and $3 million, depending on the configuration. And you do not just need one. As qubit counts scale up, the number of refrigerators required scales with them, and each refrigerator has hard physical limits on how many qubits it can accommodate. The cooling power can only handle so much heat load before the system fails. IBM's most advanced cryogenic concepts, like the experimental GoldenEye system, are the size of a large room. The electricity consumed to maintain these systems runs into megawatts annually, not for computation, but purely to maintain the cold. The global market for cryogenic support infrastructure in quantum computing alone has been valued at $1.4 billion. This is not science. This is a ransom note. And the quantum computing industry has been paying it for decades with no way out. If you think this sounds insane, smash the like and subscribe button, because what Stanford just did makes the entire cryogenic industry look like a museum exhibit. On the 29th of November 2025, a research team led by Professor Jennifer Dion and postdoctoral scholar Feng Pan at Stanford University published a paper in Nature Communications that fundamentally changes the conversation. The paper described a nanoscale optical device, a device so small that individual components are invisible to the naked eye, roughly the size of the wavelength of visible light, that performs key quantum operations at room temperature. No cooling, no dilution, refrigerators, no megawatts of electricity burning just to maintain conditions. The device sits on a chip and works at the same temperature as the room you are sitting in right now. The technology at the heart of this breakthrough is something called twisted light, and understanding it requires a brief but important detour into physics. Photons, particles of light, have a property called spin. In most optical systems, this spin is difficult to control precisely, but the Stanford team built a nano-patterned silicon substrate, an ultra-thin base layer etched with microscopic patterns that force photons passing through it to spin in a specific direction, either clockwise or counterclockwise as they travel. The photons literally corkscrew through this material. These spinning photons then interact with a thin layer of a material called molybdenum diselenide, which is placed directly on top of the silicon base. Molybdenum diselenide belongs to a family of materials called transition metal, dichalcogenides, or TMDCs, which have extraordinary optical properties at the nanoscale. When the corkscrewing photons hit electrons inside the molybdenum diselenide, they transfer their spin state to those electrons. The photons spin and the electrons spin become linked, quantum entangled, creating a stable qubit without requiring any cooling whatsoever. Like and subscribe. Because quantum entanglement just moved out of the freezer and onto a chip you could hold in your fingers. The reason this works at room temperature, and the reason it is so scientifically important, is that the material combination naturally suppresses decoherence without the need for extreme cold. Normally, thermal noise at room temperature would immediately destroy the quantum entanglement. The random jiggles and vibrations of atoms at normal temperatures overwhelm the delicate quantum state in nanoseconds. But the chiroptical cavity, the specially designed optical resonator formed by the silicon nanopatterns, creates a microenvironment that dramatically enhances the coupling between the photon's spin and the electron S spin. The research showed that the device enhanced Valley-specific radiative transition rates by a factor of approximately 13 compared to standard materials, with quantum state lifetimes as short as 189 picoseconds. That may sound brief, but in the world of quantum operations, it is more than enough time to perform fundamental quantum communication tasks. The thermal noise of the room cannot break the bond. The quantum state survives. This is the wall being broken. Fengpan himself explained the significance in precise terms. He described how the silicon nanostructures enable the twisted light, how the photons spin in a corkscrew fashion, and how those spinning photons can be used to impart spin on electrons that are the heart of quantum computing. Professor Dion added that although the patterned nanostructures are imperceptible to the human eye, they allow the team to manipulate photons with extraordinary precision, to twist them in a specific direction, either up or down, and that precise control is what makes the room temperature quantum state stable. This is not a theoretical demonstration on a whiteboard. This is a fabricated device, tested, measured, published in a peer-reviewed journal, and reproducible. Stanford did not just propose a new path around the Great Wall. They built the door, walked through it, and left it open for everyone else. Now let us talk about what this actually means for the world, because the implications reach far beyond any single laboratory or any single paper. The first and most immediate consequence is economic. The $3 million dilution refrigerator is not just expensive to buy. It is expensive to operate, expensive to maintain, expensive to install, and it requires an entire support infrastructure of compressors, pulse tubes, electromagnetic shielding, and specialized technical staff just to keep it running. Every qubit in a superconducting quantum processor carries a price tag of $10,000 to $50,000, attributable purely to the cooling complexity surrounding it. Remove the cooling requirement, and that cost structure collapses entirely. The price of a quantum processor moves from the realm of national laboratories and trillion-dollar technology companies toward the realm of universities, hospitals, mid-sized research institutions, and eventually, over years, potentially toward consumer electronics. Like and subscribe. Right now, because researchers at Stanford themselves said it. If they can miniaturize this technology far enough, someday we could do quantum computing in a cell phone. The second consequence is scalability. One of the most fundamental barriers to building more powerful quantum computers has been the physical constraints of the cryogenic refrigerator. You cannot simply add more qubits without adding more cooling capacity, more refrigerators, more infrastructure. The cooling system becomes the ceiling on how powerful the machine can ever be. Room temperature quantum devices do not have this ceiling. You can, in principle, stack components the same way classical chip manufacturers stack transistors, building denser, more powerful systems without the physical limitation of keeping everything inside a freezing cold enclosure. The scalability unlocked by removing the cooling requirement is not incremental. It is potentially generational. The third consequence is the transformation of distributed quantum systems. Today, building a quantum network, a network of quantum computers communicating with each other the way classical computers communicate over the internet, requires cryogenic infrastructure at every single node. Every quantum repeater, every quantum router, every quantum communication relay point needs its own cooling system. The cost and complexity make truly distributed quantum networks almost impossible to deploy at scale. Room temperature quantum communication devices change that calculation completely. A distributed quantum network with room temperature nodes becomes architecturally similar to the classical internet infrastructure that already exists. This is not a minor improvement in convenience. This is the difference between a quantum internet being a theoretical concept discussed in papers and a quantum internet being something that actually gets built in the next decade. The fourth and perhaps most profound consequence touches every industry simultaneously. Quantum computing's most transformative applications, the ones that researchers and governments have invested over $54 billion globally to unlock, all require quantum systems that can be deployed widely and affordably. Drug discovery is one. Quantum computers can simulate molecular interactions at a level of detail that classical supercomputers cannot match, and finding that simulation could compress the drug development timeline from a decade or more down to years. But pharmaceutical companies cannot do this if quantum computing requires multi-million-dollar cryogenic infrastructure per machine. Financial risk modeling is another. Quantum algorithms can evaluate risk portfolios across combinations of variables that would take classical computers thousands of years to compute. But investment banks cannot practically deploy quantum systems that require liquid helium cooling and round-the-clock cryogenic engineers. Artificial intelligence acceleration is a third. McKinsey's 2025 report confirmed that quantum computing directly addresses AI's core computational constraints around algorithmic efficiency and memory walls, but the hybrid quantum classical systems that would unlock this potential require quantum hardware that can sit alongside classical GPU clusters in ordinary data centers. Room temperature is not just a convenience. Room temperature is the prerequisite for all of this to actually happen. Like and subscribe, because in 10 years you may look back at Stanford's November 2025 paper the same way people look back at the first transistor. The cryptography implications deserve their own paragraph because they are urgent in a way the other applications are not. Today's internet security, the encryption that protects your banking passwords, your private messages, your government's classified communications, is based on mathematical problems that classical computers cannot solve in any reasonable time frame. Quantum computers, at sufficient scale, can break these encryption standards in minutes. This is not a distant hypothetical. The timeline for cryptography breaking quantum machines has been shrinking dramatically, and by 2026, governments and cybersecurity institutions worldwide are treating it as an imminent national security concern. The standardization of post-quantum cryptographic algorithms has already begun, with organizations racing to protect their data infrastructure before fully capable quantum computers arrive. If room temperature quantum devices accelerate the timeline for powerful quantum computers by removing the single largest barrier to their deployment, the cooling requirement, the urgency of the cryptography transition increases proportionally. This is not a problem for future engineers to solve. This is a problem the world needs to solve faster because Stanford just shortened the clock. There are challenges remaining, and intellectual honesty demands acknowledging them. The Stanford device demonstrated a key quantum communication function, entangling photon spin and electron spin at room temperature. It did not demonstrate a fully programmable, fault-tolerant quantum processor. The leap from this device to a commercially deployable room temperature quantum computer still requires significant engineering progress in qubit control, error correction, and system integration. The researchers themselves noted that supporting components, better light detectors, integration protocols, manufacturing processes, all need to be developed. Stanford estimates that quantum in consumer smartphones is likely more than 10 years away, and that estimate is described as optimistic. Practical quantum advantage in narrow domains like drug simulation and financial optimization could arrive in 5 to 10 years, but that timeline is contingent on engineering execution across an entire ecosystem of technology development. That said, the significance of what Stanford accomplished is not diminished by what remains to be done. Science advances through precisely this kind of breakthrough, a fundamental proof of concept that demonstrates a new path is possible, that the physical principles allow it, that the materials and mechanisms actually work. Every major technology we rely on today passed through exactly this stage. The transistor was demonstrated before anyone had built an integrated circuit. The Internet protocol was proven before anyone built Teehee World Wide Web. The lithium-ion battery chemistry was validated in a laboratory years before it powered smartphones. Stanford's room temperature quantum device is that moment for quantum computing. The Great Barrier has not just been theoretically challenged, or it has been experimentally defeated. Like and subscribe, because you just watched science change the trajectory of an entire technological civilization. The researchers are already working on next steps. Professor Dion and Feng Pan are exploring other TMDC material combinations beyond molybdenum diselenide to achieve even greater quantum performance, and they are investigating pathways to integrate the device with existing semiconductor manufacturing infrastructure. The compatibility with silicon, the same material that underpins the entire classical computing industry, is not accidental. Silicon. Compatibility means that the fabrication techniques, the supply chains, the manufacturing expertise that already exists for classical chips could, in principle, be adapted to produce quantum devices. This is the kind of industrial leverage that transforms a laboratory breakthrough into a civilization-scale technology. The quantum computing industry entered 2026 at a genuine inflection point. IBM was racing toward quantum advantage targets with thousands of qubits. Google had demonstrated exponential error suppression with its Willow chip, achieving a 13,000-fold speed-up over the Frontier supercomputer for specific physics simulations. Governments had committed over $54 billion in cumulative public investment to quantum technology development. Private rounds worth hundreds of millions of dollars had flowed into companies like PsiQuantum and Quantinuum. The entire global ecosystem was accelerating. And then Stanford published a paper that ripped away the single most fundamental constraint holding the field back. The room temperature barrier, the wall that everyone assumed would take generations to climb, has been crossed with a device built from a thin sheet of crystal on a nano-patterned silicon chip. What happens next is a question for engineers, investors, governments, and the companies already racing to build the quantum future. But the physics is settled. The proof exists, the device works. And for the first time in the history of quantum computing, the most expensive and most limiting requirement of the entire field has been eliminated. Not worked around, not reduced, but eliminated at room temperature on a chip in a laboratory at Stanford University. The machines that once needed to be colder than outer space can now, in principle, run at the temperature of a quiet room. And that changes everything. If this blew your mind, do yourself a favor. Like this video and subscribe to this channel, because the quantum revolution is just getting started and you do not want to miss what comes next. The story of quantum computing has always been a story of barriers. Every 5 years, some new barrier appeared that experts declared fundamental, permanent, and insurmountable. The noise problem, the error rate problem, the qubit stability problem, the manufacturing problem, and towering above all of them, the cooling problem. The requirement that these machines exist only inside environments so cold that the laws of thermodynamics themselves seem like obstacles. One by one, researchers have chipped away at these barriers, but the cooling problem stood apart. It was not a software issue that clever algorithms could route around. It was not a manufacturing challenge that better fabrication tools could solve. It was physics, the fragility of quantum. States in the presence of thermal energy seem to make extreme cooling a permanent, non-negotiable fact of quantum computing. That is what made Stanford's approach so counterintuitive and so significant. Instead of fighting the thermal environment, instead of trying to suppress it through brute force cooling, the Stanford team built materials that naturally resist decoherence at room temperature. They found a way to make the quantum state robust enough to survive in an ordinary room. This is not engineering around physics. This is engineering with physics, finding material combinations and geometric structures that use the same quantum mechanical principles to stabilize the qubit state that classical engineering has always relied on temperature suppression to achieve. This conceptual shift from managing the environment to building materials that dominate over the environment is perhaps the most lasting scientific contribution of this research. It suggests that the entire design philosophy of quantum computing hardware may be at a turning point. For 30 years, the dominant paradigm has been build your QBI-T system, then engineer away every possible source of decoherence, starting with temperature and working outward. The Stanford result introduces a different paradigm. Build your qubit system so that the quantum coupling is so strong that moderate environmental noise cannot break it. This has enormous implications, not just for cooling, but for every other source of decoherence in quantum systems. If materials can be engineered to resist thermal decoherence, the same engineering principles may lead to materials that resist electromagnetic interference, mechanical vibration, and cosmic ray hits, all of which are additional sources of qubit error that the quantum computing field is struggling to manage. Like and subscribe, because the biggest revolution in computing history is unfolding in real time, and most people have no idea it has already begun. For ordinary people, watching all of this unfold, the question is simple. When does this change my life? The honest answer is not tomorrow and not next year. The engineering path from a nanoscale research device to a mass-manufactured consumer quantum chip is long and filled with obstacles that cannot be predicted in advance. But the direction is clear in a way that it was not before November 2025. Before this paper, the question of whether quantum computing would ever escape the laboratory and reach the scale of ordinary technology was genuinely open. The cooling requirement was a civilizational barrier, not in the sense that no progress was being made, but in the sense that every step forward still required the same fundamental infrastructure of cryogenic containment. The barrier is now gone in principle. What remains is engineering. And engineering, history has shown, is something humanity is extremely good at when the destination is clear and the physics permits the journey. The destination is clear, the physics permits it. Stanford just handed the engineers the map.